In terms of the volume of cargo in the Arctic, modern Russia significantly surpasses the Soviet Union. That's why even more powerful vessels are rushing to help the existing icebreakers as part of the 420 project, as the professionals call it. The lead icebreaker, Arktika, left the slips of the Baltic shipyard in St. Petersburg in May of 2020. Soon, two other similar vessels are to join it, Siberia and Ural. These are the largest icebreakers in the world, over 550 feet long. Electric motors with a total capacity of 60 megawatts, or 81,577 horsepower, allow the ship to break up ice up to 9.5 feet thick. But alas, even this isn't enough for high-speed crossing of the treacherous northern seas. The LEADER project, whose name speaks volumes, should bring Russia into a leading position in the field of maritime transport, ensuring year-round shipping along the northern sea route.
The LEADER icebreaker is an integral part of the program for creating an Arctic fleet that can secure the Eastern Transport Corridor. For Russians, this is very important. Why? Because we have to have a corridor for the delivery of our hydrocarbons from the Yamal Peninsula, from Dudinka to, well, first of all, to the Asian market. The corridor has to be independent from the sanction policies of the leading countries there.
The plans for the management of the Northern Sea route are ambitious. By the year 2030, Russia must deliver at least 70 million tons of hydrocarbons per year to the growing markets in Southeast Asia. For this to happen, tankers and gas carriers must continuously be going along the new route.
Today, the majority of cargo is transported through the Suez Canal from Europe, but transportation through the Northern Sea route is in fact 2 times shorter in length. But here you can say the distance itself, it's the speed of transportation that is the deciding factor. That's why a commercially effective speed of transportation is somewhere around 10 to 12 knots, no less, and all the better if it's more. Accordingly, in order to ensure that all areas can be passed, a suitable icebreaker is needed which will be able to reach that commercial speed. This task will be achieved by the LEADER icebreaker.
Moreover, due to the large mass of modern tankers and gas carriers, not only are traditional routes being considered, but also high-latitude routes where the ice can get up to 8 feet thick. The Central Design Bureau Iceberg did the calculations. To work in such extreme conditions, a vessel would be required to have a displacement of 70,000 tons with a nuclear installation with a capacity of 120 megawatts. That is twice as much as what the Arktika-class icebreakers can boast. Therefore, the written 400 reactor was developed specifically for the LEADER by OKBM Afrikantov in Nizhny Novgorod. Its thermal power can reach 315 megawatts. Each icebreaker will have 2 such reactors.
Rhythm 400 is a new type of icebreaker installation due to the fact that it is, as it were, more powerful, let's say. Before, in order to gain the same amount of power, 4 reactors would have been needed. And now we're down to 2. It'll be significantly cheaper. Again, I repeat, we work in a commercial environment, so to speak. And that's why economic efficiency is extremely important for us to ensure.
The principle of the reactor's operation is quite simple and remotely resembles the principle of operation of a steam boiler. As a result of chemical reactions, thermal energy is generated which heats water. Steam is then created which spins the turbines of the ship's power plant.
When it comes to electrical equipment, their power source is turbine generators. The power output of each turbine generator is 37 megawatts. There are 4 such generators, and the voltage of the generators is 10.5 kilovolts. The total power capacity is 150 megawatts. In Russian shipbuilding, there is no other power station that reaches that level.
Such colossal amounts of power require the icebreaker to have 4 electric propellers, 30 megawatts each.
On this icebreaker, we, for the first time, probably in all of icebreaker construction, we use 4 electrical propellers. Prior to this, only 3 propeller motors were used. Due to the fact that the power output of the propellers is 120 megawatts, we had to solve a number of problems associated with how to convert the energy from such high-powered propellers. We had to adjust the diameters of the propellers, which are also much larger here than on previous icebreakers.
All the bulky and complex technical stuffing ultimately influenced the size of the vessel. The LEADER will be the largest nuclear icebreaker on the planet, 650 feet long, roughly 2 soccer fields, with the height of a multi-story building. Plus, the LEADER will also be much wider than all previous icebreakers.
How was the width of the leader icebreaker's hull chosen? It was designed to clear the way for ships with a hull width of 160 feet. The width of the icebreaker itself is about 150 feet, but the channel that will be left behind the leader icebreaker will be about 160 to 170 feet. Thus, large tonnage vessels such as the Yamal Max, which is currently exporting gas from the far north, will be able to move freely in the channel behind the icebreaker without having to break up any additional ice at the edges.
Still ahead, why do designers create miniature models of icebreakers? How are they put to the test in ice pools? And to what purpose is a model of the ship placed in a wind tunnel? Krylov State Scientific Center in St. Petersburg. All Russian icebreakers, or rather their models, were tested here.
There is a certain modeling criteria that we meticulously follow in our scale testing. The scale of the model is chosen. It's based on the selection of ready-made propellers, which correspond in scale to the size of the full-scale propellers. As soon as we select the proper propellers, a model of the icebreaker's hull is created.
A 5-axis engraver and milling machine assists the staff of the research center. The parameters of the icebreaker are first uploaded into its electronic brain. After that, the machine independently, layer by layer, carves out the shape of the future ship. The model is then equipped with propellers, an electric motor, steering equipment, and is sent to one of the test pools, in this case, the ice pool. Cryogenic installations are used in order to freeze a layer of ice on the surface of the salt water from 1/2 inch to 4 inches thick.
The ice cover in the pool is also modeled accordingly, taking into account the appropriate scale. The thickness of the ice cover is calculated. The strength parameters of the ice are calculated. That's why our ice may seem thinner or less durable, because its strength is reduced however much is necessary so that it corresponds to the scale chosen for modeling.
Today, towing tests of an icebreaker model are being carried out in the pool, but with working propellers. This is how experts evaluate the effectiveness of the hull shape and how the ship's propulsion and steering equipment interacts with the ice cover. And of course, in real-life conditions, the icebreaker's propellers will have to literally hack through huge slabs of ice. The machinery must allow for a large margin of safety. In practice, it is not uncommon for an icebreaker to be unable to pass through a difficult section of ice covered with significant hummocks. In that event, the ship will turn to the side and simply chop the ice like a carrot with its propellers. By the way, Russian scientists from the Central Research Institute Prometei have managed to create an innovative, high-strength steel alloy that is resistant to critically low temperatures, special for the modern icebreaker fleet, and the newest Arctica icebreakers are equipped with propellers made of this material. Innovative alloys will also be used in the construction of the leader so that it can work in even the most difficult conditions.
When we were testing the leader icebreaker, the first and most important objective was to determine, as in all experiments, the maximum ice-breaking capacity of the ship. And actually, the maximum ice-breaking capacity of the leader icebreaker is very high when compared to the existing icebreakers in the world. It's at around 13 feet, but that's only at a speed of 2 knots. Still, the main task of this icebreaker is to be effective in escorting transport vessels along the northern sea route. We thoroughly investigated this goal in the ice pool. We perfected the shape of the hull. We selected propellers that would provide the amount of thrust this icebreaker requires. And based on the results of our research, we have ensured that the icebreaker is capable of moving at a speed of 12 knots, an economically efficient and beneficial speed through an ice cover 6 feet thick.
It's very rare to come across ice 6 feet thick on the northern sea route, but the leader is up to the task in any event. Thanks to the innovative pneumatic compressor system on the icebreaker, it's able to pass through difficult sections without having to reduce its speed.
On the icebreaker, on this one, there are 2 sufficiently powerful compressors that can discharge air underneath, in the area under the icebreaker. This leads to a reduction in friction due to the fact that the air bubbles are running along the icebreaker's hull. And it produces a rather good effect, and the ice-breaking capability increases even further, especially when it comes to snow-covered ice, which can be the hardest for an icebreaker to overcome.
Arctic icebreakers often have to move through fields of broken ice as well. Model tests are also carried out with those conditions in mind in order to determine the speed of the ship under different conditions.
The thing is, we're not just collecting data to assist in the design of the ship or for determining the appropriate shape of the hull. The data that we get from the ice pool is also used in developing a marine transportation system. That is, in the future, when they're developing the marine transportation system, they need to know what traffic parameters they'll be dealing with based on certain ice conditions at different times of the year, for example. So what speed the ship will move at, how much time will it need in order to get from one point to another, while at the same time conducting a caravan of ships behind it. That means all of these issues are being worked out right now in the ice pool during testing.
And over in another testing pool, the seaworthy one, the ability of the leader icebreaker to withstand waves is put to the test. For that, it was essential to prepare an exact copy of the future icebreaker.
This model, it's a reduced but exact copy of the leader icebreaker. It's 63 times smaller than the actual ship, but even then, the scale of the mass and inertia characteristics are also accurate. The weight of the model, its center of gravity, its amount of inertia.
Electric wave generators at the site allow for the recreation of storms, those that are possible anywhere in the world's oceans, naturally also scaled down to size. Icebreakers are powerful and sturdy ships, but as a rule, they're not meant to spend significant periods of time on the open sea, where there isn't any ice and storms can occasionally occur. When it comes to the leader, the designers attempted to eliminate this shortcoming.
Those ships that have good ice-breaking capabilities, as a rule, rank much lower when it comes to seaworthiness. Here we were presented with the task of finding a solution. How can you not reduce ice-breaking capabilities and at the same time increase the seaworthiness of the ship? We were able to reach a compromise, and the leader icebreaker handles itself well on waves that rate as high as 6, 7, or an 8.
This is important not only in terms of the survival of the ship and its speed, but also for the comfort of the crew.
Because of course, again, the less the ship is pitching, the less its acceleration, the better the ship's crew will feel. Nobody wants to lay there when there are extreme waves hitting the ship or suffer from seasickness. So this is also about taking care of the crew, those people who will be working on the ship.
The experience of the specialists at the Krylov State Scientific Center says that the data accumulated in the pool tests is around 99% accurate in its representation of the data that will come from real-life testing out in the open sea.
Clearly, some of the conditions here are more ideal. Clearly, in real-life conditions, wind is going to be a factor. But that's already one of the many nuances that, of course, depend on the exact point you are in the ocean.
In fact, gale force wind can actually also be simulated in the testing center in a landscape wind tunnel. Here, the adverse effects associated with airflow are identified and investigated. A smoke machine allows the specialists to see the way the air flows around the hull of the ship.
The analysis and evaluation of the controllability and maneuverability characteristics of the ship are based on this information. The second important goal is to study the wind fields around the landing pad on the ship. Since this icebreaker has a very large and developed structure to it, large detached zones are formed in its wake.
To put it simply, turbulent wind swirls over the landing pad, and that could lead to a terrible tragedy.
Standard helicopters like the Mi-8 or the Ka-32, for example, they have their own limitations when it comes to vertical speed. If it's too much, the Mi-8, for example, can cut off its own tail section with its propeller. And the Ka-32, which has two propellers, can simply twist one around the other. Accordingly, during the design stage of this icebreaker, all these studies were carried out, and we identified numerous negative things that are related to aerodynamics. For example, in standard mode, it would have been impossible to use the Ka-32 helicopter because of the very strong and large slanted streams. To get around that situation, we suggested that the designers either raise the helipad higher and move it out of the way of these adverse streams, or to place special deflectors near the platform that would be able to smooth out the flow of air.
In comparison to classic nuclear-powered icebreakers, the leader has a much more aerodynamic shape to it. It's very smooth, streamlined, and that was not done so much for the sake of aesthetics as much as for the sake of simple economics.
If the structure, one on this grand scale, hadn't been so elegantly laid out, if it had been like the Arctica-class icebreakers, then of course all the issues that we identified, the aerodynamic ones, they would have been ever more difficult to solve, more of a problem. Eliminating them would have taken even more time and more money as well. That's why the excellent contours of this ship, from the point of view of aerodynamics, they aren't only a tribute to style or beauty, they're excellent and correct technical solutions.
The data collected in the wind tunnel is then entered into the Scientific Center's supercomputer, and a special program allows for simulations of a helicopter landing on the icebreaker under a variety of wind and weather conditions to be carried out. Still ahead, what safety systems are used on modern icebreakers? Why aren't hull breaches a threat to the leader? And how will this innovative project help the development of the far north? Nuclear-powered vessels still raise concerns among some environmentalists. They fear if an accident occurs, the ocean will be contaminated with radiation. But when it comes to icebreakers, these fears are unfounded. Modern reactors have multi-layered protection. Not even a fire on the icebreaker threatens them. As for the leader, it will have the most modern fire extinguishing and reactor protection systems available installed on it. The most important innovation is the nuclear installation's cooling system, which is capable of working even in the event that all power is lost on the ship.
This is a new solution, and it will be used for the first time on this icebreaker. It didn't exist on previous icebreakers. It's possible thanks to air. In effect, it's an air-powered heat exchange, which due to the natural thrust allows the reactor to remain cool.
Hull breaches are also nothing to fear. After all, like all modern icebreakers, the leader has a double hull. That's why even in the event of a collision with another ship or a submarine, the icebreaker will remain afloat.
On this particular icebreaker, just like on previous ones, we've included structural protection against a collision with a smaller type of vessel. We've included structural protection against helicopter crashes, against running aground. That is, generally speaking, we've looked at all possible accidents, calculated the theoretical consequences, and then looked at certain structural solutions that would allow us to either eliminate the issues or to at least minimize the damage that could occur.
All of these situations are played out on the supercomputer. It's impossible to design a modern icebreaker without 3D modeling. Engineers and designers work with the electronic copy of the future vessel. With it, they can carry out the majority of necessary adjustments and complex calculations.
Included in that is the large concentration of electrical equipment, which of course generates electromagnetic fields that affect the electromagnetic compatibility of equipment, control systems, landing systems of aircrafts, the capabilities of communication equipment, and so on and so forth. Vibration parameters, sound parameters, they're also developed by corresponding models, only within the given parameters.
A large variety of specialists work with the virtual design model: power engineers, electricians, communication specialists, architects, and so on.
It's a complete model which can be broken down into several pieces. Like wood, it splits into a very, very large number of components, and in the end, you're left with a complete design model, and accordingly, each of the components are optimized individually. You probably never would have thought that the overall mass load, which determines the mass of the icebreaker, is also taken into account, and it comes out to around 3.5 to 4 tons. Even the mass of the air is taken into account.
High demands are also placed on life support systems on the vessel. After all, in agreement with established practice, the crew spends 4 months on the icebreaker before it's replaced by another team of specialists.
In order for people to feel comfortable enough, single-person cabins are provided. Those are provided for the entire crew. Those single-person cabins. A sufficiently extensive athletic area is provided. We have a gym, we have exercise machines, we have a pool, a sauna. There is a fairly developed block of public spaces. Included in that is an observation deck. There's even a bar. There's a conference room of sorts, meaning people can live well-rounded lives for a fairly long period of time here.
At the same time, a crew of just 60 people is enough to fully man the massive vessel.
By the way, there is another one of our new decisions. We're forced to look seriously at questions related to automation, and with that in mind, we were able to reduce the crew number even in comparison to the 22-220 Icebreaker project, essentially the new Arcticas. There, the project worked out to require a crew of 75 people. Of course, the smaller the crew, the smaller the operation costs of the ship, and the more cost-effective the Icebreaker becomes.
The designers also provided for the possibility of taking on board a personnel of up to 150 specialists. A large reserve in regards to both capacity and provisions was accounted for. There's enough food for everyone for 8 months. The project follows the ideology that the people who explore the cold and unfriendly Arctic should be living in the most comfortable conditions possible. Ultimately, their efforts will have a positive impact on the overall cargo turnover of the Northern Sea Route. Russia will be able to increase not only in its amount of shipments, but also profit from ensuring the passage of foreign vessels.
Accordingly, we're moving away from the mode of delivering hydrocarbons in this climate zone, which I call an increased risk, to a scheduled mode of operating where the risk of getting hit by penalties from the customers is reduced to zero. We will, in practice, have the same sort of schedule that exists for railways. This is very important for Russia, for its status and for its economic security.
Construction of the Leader icebreaker began on July 6, 2020 at the Far East Zvezda shipbuilding complex in the Primorsky territory. The new icebreaker is set to be put into service in 2027, and then the managers of the Northern Sea Route will assess the traffic of the transport artery once again. If the route across the Arctic Ocean is in high demand, then construction will begin on 2 more nuclear-powered vessels of the Leader type. They are extremely expensive ships. The maximum cost of the first-ever Leader icebreaker is around 127.5 billion rubles, or roughly $1.65 billion. But as is the case with all cutting-edge projects, the creation of such advanced equipment should raise the number of involved Russian enterprises to a higher level of operation and ensure they are then receiving orders for years to come.
Just so you understand what we're talking about here, when the 22-220 project began, we didn't have any enterprise in the electrical industry that could create engines of this class. This is really a sector that, with its development, it creates jobs in shipbuilding. It creates maybe 7 there, then 10 jobs in other sectors related to the development and supply of equipment to the ship.
The modern port of Sabeta is one of the pivotal points of the Northern Sea Route in the 21st century. To be more exact, it's a monoport. Its focus is the shipment of liquefied natural gas produced on the Yamal Peninsula. Deliveries to the west are already in full swing, and in the east, Russian gas is needed by China, India, Japan, and South Korea. Soon, a number of similar ports should appear in the Arctic seas. Just as the Silk Road in ancient times created rich trading cities, so the Northern Sea Route should stimulate the development of Russia's far north. But first, the largest and most beautiful icebreaker in history needs to be built. It's a good thing that Russia has the scientific and technical potential to tackle this ambitious task.